right, we ended the other day on this right here, so I want to go back and hit one more time to talk about the high points of it. Valence electrons. What are valence electrons? Outer shell. Okay? You need to know why valence are so important. And here is why they're important. Is because these are the electrons that can be lost, gained, or shared between atoms. Which means they do what? They are the ones that are bonded, if it will write the letter D. These are the ones that are bonded. So when we get into the very next chapter, after we get back from Christmas, we're going to talk about the electrons that actually go through bonding, and it's the valence electrons. So the electrons that interact in this manner are those in the highest energy levels. Really, it's the orbital that is farthest from the nucleus. Okay? Farthest from the nucleus. Now, again, the trend you're going to need to know about the valence electrons. This is very simple. Electrons available, lost, gained, or shared. Incompletely filled most of the time. What is the only group that's full? Very good. So the only... all but Ng. What is Ng? Noble gases. So all of them are incompletely filled except for the noble gases, because the noble gas is the only group that's full. Now, here is your trend for the group, and you're definitely going to need to know this. I hate this slide so bad. Okay? All right. So, do you notice as we go down the column, do you agree that that's really moving left to right on the periodic table? Group 1 through 18. What is happening as we move left to right with our valence number? Okay? All right, so that's what I want you to put. As we move left to right, it increases. Okay? That's easy. Yeah, okay? It's easy. Here's the other thing. As you go from top to bottom, this is the one that you need to pay attention to. This is the one that's going to catch you if you're not paying attention. If I go from lithium to sodium to potassium, did I stay in group 1? How many valence electrons do they have? The same. Very good. So as you go from top to bottom, it is the same. It does not change. Okay? It's very important that you recognize that. As you go from left to right, they increase, but as you go down, it stays the same. Okay? Any questions there? All right, so that is your valence electron. All right, we're going to try to cover 2 of the other trends today. The other trend that we're going to try to get to is called ionization energy. All right, first of all, what is ionization? The process of becoming an ion. Well, that's easy. What is an ion? Has a different number of electrons. Okay? There are 2 kinds. There's a positive ion and a negative ion. What is a positive ion called? Cation ion. A negative ion is called anion. How do you become a positive ion? Lose one. How do you become a negative? You gain. Perfect. Y'all are awesome at this. So, again, an ion is an atom or a group of bonded atoms that has a positive or negative charge. Do me a little favor, and where it says a group of bonded atoms, please write the word polyatomic. Y'all know what polyatomic is? Yes, you better know what those are. Those are coming back around again soon, I promise. So, again, what did you notice about all of the polyatomics? They were charged, right? Nitrate was NO3, negative. Sulfate was SO4, 2 negative. Phosphate was PO4, 3 negative. Ammonium was NH4, positive. Good, NH4 positive. So again, those are charged polyatomic ions, okay? So, again, the electrons change. Sodium, for example, easily loses an electron to form sodium positive ion. Why does sodium easily want to lose an electron? It's group 1, so it can turn into a noble gas. Very good. This forms a cation, which is a positive charge. So the process that results in the formation of ion is called ionization. So anytime you ever add the word ation to the end of something, that means the process of. Well, ionization is the process of turning into an ion. Now, this is where you need to put the little star. The very last bullet. This is like if we were to look it up in Webster's dictionary, this is what it says. The energy required to remove one electron from a neutral atom is called the ionization energy. Well, duh, if an ionization is the process of becoming an ion, does it require energy? Yes. Do you think some atoms require more than others? Yes, and that's the trend we're going to have to talk about, is what really happens whenever we're trying to remove. Keyword here, if you're highlighting words, keyword here is to remove an electron. How much energy is required to remove? Now let's talk before we even get into it. Which group really wants to get rid of their electrons? Group 1. Which group really wants to gain one? 17. So which group out of those two will probably have the higher ionization energy? Which one would it be really hard to take one from? Fluorine is the hardest one. Very good. So the halogens. So let's think about it. So if they have 7 valence electrons, how many more do they need to be stable? Just 1. So if they can gain that 1 more, what are your chances of taking 1 to knock it back down to 6? Very slim. And so that's what we're trying to calculate, is how much would it require. All right, so in general, we already know this, and you knew this without even realizing that this is where we were going. In general, why does it say in general? Are there some weird oddballs? Yes, guess what? We don't have to know those. Fantastic for us. Ionization, no, we don't ever have to know this because I don't even know what they are. In general, ionization energies of the main group. Let's pause right there and let's make a little note, because I said hint, hint, wink, wink whenever we talked about this. What are the main groups? S and P. So what 2 blocks did we leave out? D and F. We're just talking about group 1 and 2 and then 13 to 18. We're not paying any attention to the D block and the F block. So just those groups increase across the period. Can a 4-year-old learn that fact? Yes, you guys are in high school. You need to learn the reason why. The reason why the ionization increases, which means the amount of energy required to remove an electron, is caused by an increased positive charge. Now, how do I increase my positive charge? You have more protons. Okay? Think about it. If I go from lithium, it has 3 protons, to fluorine, it has 9. Did it go up? Well, that's easy to think. So because we have a higher charge, it more strongly attracts the electrons. Every bit of that in purple, what does that sound like? Very good. It sounds just like Zeph. So, but the more protons we have, the higher our what gets? Zeph. So the reason that the energy goes up is because what goes up? Zeph goes up. And what is Zeph? Not a charge, but an attraction. The ability of a nucleus to have an attraction on what? Valence electrons. Perfect, okay? Now, metals lose electrons more easily than nonmetals. When they lose them, what do they turn into? Cations. Very good. And that's something that I really hope you see as a trend happens. What is the name of group 1? Alkali metals. What is their charge? +1. Group 2 is the alkaline earth metals, and their charge is +2. Notice plus, all of the transition metals will be plus something. Now, I've mentioned this, transition means to what? To change. They can be different ones, and we'll get into that. Nonmetals lose electrons with difficulty. Because it says with difficulty, what do you think their amount of energy will be? High energy, way up there. Okay? High energy, way up there. And you're going to see that in just a second. So, Again, so what happens is we go down. Again, main group. We're talking about S and P. As we go down a group, ionization energy is generally what? And there's one major factor. Why? What is an easier way to say that? What's an easier way to say that? Why would the valence be getting farther from the nucleus? Adding more orbitals, which means they're getting bigger and bigger and bigger. Very good. So they are getting larger. Okay, they're getting larger. They are getting larger. So the electrons are removed more easily. Again, let's go back to the situation up there with Swingluff and the kindergartners. Okay, if you have 10 kindergartners running around your feet, would there be a certain amount of energy required for that 11th one to climb the fence and get away from you? Yes. Do you agree that you could pretty much spot that 11th one crawling over the fence? It'd be difficult, but you could do it, right? Okay. What if I have 54 kids running around your feet? How much energy would that 55th kid in comparison to the 11th kid have? Basically, it would be so easy for him to leave, right? So, he could basically say, see you, and walk right out the gate, and you'd never know it. So, it's less energy expended. Why? Because you're distracted. What are those distractor electrons in the middle called? The shielding, and they're called the core electrons that are shielding. Perfect. They're shielding your viewpoint, okay? What if we went all the way down to lithium? You'd only have 2 kids. How hard would it be for that one if you only have 2 kids running around? It'd be almost impossible, right? He would have to do all kind of crazy tricks to get away from you, and so that's kind of the situation you can think about it in. Okay. Now, this is a basic energy equation. Ionization is an endothermic process. So let's start right there. What does it mean to be? What was that for? Endothermic. What does that mean? Very good. So we talk about energy. It's kind of funny you said that because we're in thermo right now in AP Chemistry, and I'm completely flipping the script on what hot and cold means. Yeah, you do. If I have enough time at the end of class, I'll tell you. Okay? All right, so energy goes in. So here's the concept. Energy has to be supplied. In terms of a reaction, of a chemical reaction, what are the 2 parts of a chemical reaction? Okay? Products and reactants. Really, it's semantics of how you say it. Reactants make products. So it's reactants and products. If energy is required to go into the reaction, would it be a reactant or would it be a product? It would be a reactant. So notice this, that energy is on which side? The reactant side. Everybody okay with that? Okay. This letter A, is it charged or is it neutral? This letter A, the first one, the leftmost. Okay. This is neutral. Okay. Do you agree that the other letter is charged? What do we call something that's charged? An ion. Now, specifically, this is positive, so it's what kind of ion? A cation. Now, do you agree that ionization energy is the ability to turn something into an ion? This one, did it gain or did it lose an electron based on where the electron is? Lost. It lost an electron because, one more time, the definition of ionization energy is the energy required to remove an electron. Are we taking away an electron? Yes. Now, letter A represents any atom, right? Depending upon what atom is sitting here, does your amount of energy change? Yes. Okay? So, the value for ionization energies are always positive. Please highlight that. Make sure you know that. They're always going to be positive. Why? Because energy does what? Energy is in. Okay, it's got to be added to it. It's got to be added to it. Metals have low ionization energy. Non-metals have high ionization energy. So according to this, which one is easier to take an electron? Metals, because they have low. How did we know that? But why? Why do metals have low ionization energy? What do they want to do with their electrons? They want to get rid of them. That's why they're really low. The higher the energy, the harder it is to remove, the more energy is needed. That's why it's in that perspective. Okay, so let's look at a few charts. Now, we're comparing group 1 to which group? And don't say 8. 18, very good. What do you notice about the comparison from group 1 to group 18 in terms of the ionization energies? Is it a lot more? Yes. Real quick, what is kJ per mole? Kilojoules. What's kilojoules? It's a unit of energy, right? Kilojoules are your unit of energy. So, if we look at it, lithium is in which row, is what noble gas is in the same row as lithium? Neon. So let's compare as we go lithium to neon. Do you agree as we move left to right, that amount of energy went way up? Hey, Austin, pull that door too for me, please. Do you agree that amount of energy went way up? Yes. Okay. So, now let's talk about it as we do this. As we go left to right, as we went left to right, as we went across the periodic table, what happened to our ionization energy? It increased. Because our Zeph increased. Okay? So we moved left to right, it increased. Now, let's notice a theme. As we go between the groups, as we stay within group 1 and group 18, what do you notice happens to your values? It goes what? Down. Very good. So as we go top to bottom, ionization energy does what? Decreases. Because why? Larger. They're getting bigger. According to this table, which one has the highest ionization energy? Which one requires the most amount of energy to pull an electron from? Why would it be helium? It's got one orbital, which means what in size-wise? It is the smallest, and what? Okay, all right, that's a great question. The reason why it's not smaller, hydrogen is 1 proton on 1 electron, right? Helium is 2 protons on 2 electrons. Which one would pull a little stronger? No, yes, but it's 2 on 2. 2 will pull stronger than 1. It's a ratio of 1 to 1, but the strength of attraction goes up because each proton-electron pair has a strength of attraction, so it's going to pull a little bit closer. Does that make sense? Because you got to look at it individually, because each one has a strength of attraction, and it's going to make it come a little bit closer. So helium is going to be the smallest, or the greatest, highest energy. Okay. All right. Here's another little chart you can look at. Larger. All right. Here's something else I want you to take a peek at, and again, this will make sense. Once we're finished, I know this is kind of convoluted. All right. Do you agree that the lines that I have green highlighted are the different periods? So hydrogen to helium, that's row 1. Lithium to neon, that's row 2. Sodium to argon, that's 3, and then so on. What do you notice about these trend lines, what happens? What happens to the slope? It gets less and less positive, right? So this is almost a 90-degree positive slope. So then it gets a little bit less positive as we go. Why? Say it again. Zeph is decreasing and the size is getting bigger. So these down here are the largest of the atoms. Okay, these down here, these are the largest. So again, it should make sense why it should require less and less and less. What do you know? Again, I'm just going to kind of mess this up. It's a purple. Okay, what are all of those? Those are all the noble gases. And let me change it to orange. All of these are those are the alkali metals. Those are all group 1s. And so that's how it's going to work. Now, there are a few odd things that show up here. Let me kind of highlight. Again, there's more than what I'm going to highlight, but there are a few. It's going to be there, 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 and there. What do you notice about all those red dots? They go up, and then what happens? They go down just a little bit. Again, that's why when we said in the beginning, generally it has that effect. But as you can tell, are there a few oddities in there? Yes, but we don't have to know those. That's why we talk about general trends. There are exceptions to every single rule, and there are a few, but we don't have to know what they are. Okay? All right. Does this make sense? Can you see the pattern developing? What's happening to the size of the blocks as we move left to right? Definitely getting taller and taller, right? So that means the amount of energy is increasing. Okay. What's happening to the blocks as you go down? They're getting shorter. So, where is your tallest, largest block? Helium. Where's your shortest, smallest? So, do you see how the trend works? Okay. You see the trend there. All right. Last little picture for ionization energy is this one. Here's what I want you to know. What did I write earlier? And that was because it was a good way to explain this. Okay, that's right. All right, so here's what I want you to write. I want you to write that underneath that. The more electrons that are removed requires more and more and more energy. The more electrons that are removed requires more and more and more energy. And you should see kind of a theme here showing up. All right, what group is sodium in? Let me stop right there. Let's talk about something else. This I1, I2, I3, I4, I5, all the way to I7. This I stands for ionization energy of 1 electron. What do you think 2? So the second electron, and then 3rd, 4th, 5th, all the way to 7th. Okay? So, sodium is in which group? Group 1. So how many does it want to lose? It wants to lose 1. Do you agree that that is the lowest number up here on this chart? What all of a sudden happens when you want to try to take that second one? How much does it jump up? A lot. Right? You see that? All right, what group is magnesium in? So how many does it want to lose? If it's in group 2, it wants to lose 2. So from the first one to the second one, it almost doubles, right? Or it pretty much does double. But then what happens when you want to try to take the third one? It shoots through the roof, right? All right, what about aluminum? It's in group 13, so how many does it have? Group 13 has 3. So does it want to gain? Does it want to lose 3 or gain 5? Lose 3. So 1, 2, 3, and then notice what happens after the third one. What does the number do? It jumps way up. So you're starting to see a theme here. What do you see the theme as being? Perfect. What is, after this stair-step line, what has it achieved? Stability, but we call that an, is it a question or statement? Okay. What do we call that? All right, so here's what I want you to write. Yes, octet. All right, so here's what I want you to write. So the stair step, S's are the worst things to write on these boards. Alright, so after that stair-step line is when the atom gets an octet. It is stable. It is sufficient enough to maintain. So that's why the energy levels shoot through the roof, is that you're not going to get any more of its electrons. Let me give you a real life. Okay, Nick, go ahead and ask your question. It only has one valence electron. It's, you sure? Okay. All right, let's just pretend for just a second that I'm sodium. And I got a bag of Cheez-Its. No, you can't have them. If I have one valence electron, what group am I in? I'm in group 1, right? If I were lithium, in terms of the size, where do I need to place this? Bag of Cheez-Its. Like, this is my valence electron. If I'm lithium, the highest group 1 metal, in terms of distance, where do I need to place this thing? Closest or farthest? Closest to me. I only have 3 electrons, one of my valence is closest, right? If the bell rang and you all decided to run out to lunch and someone tried to grab that right there, how hard would it be? You want a broken finger? Okay. So, what happens as I go down to sodium? What has to happen to this bag? It's got to get a little bit farther, right? Okay. Then I go down to potassium. As it moves out, what has just happened? Okay, let's talk about ionization energy. Ionization energy is the energy required to remove it. How much energy are you going to have to expend when it went a little further out? Less energy, right? Okay, what happens when I go to potassium? It goes further out, and you use more or less? Less energy. Let's go all the way down to cesium. Now what happens? Do you have to hardly expend any energy to get this thing? Not at all, right? So do you see the distance relationship here? The farther out it gets, the easier it gets. You with me? Now, what happens when I go back to beryllium and I add a second bag? Quit getting big-eyed. Okay? Now, is it possible to take 2 of these? It's possible, right? There's 2 available. Okay? The closer it gets, do you agree it's rather difficult to get there? Okay? So if you get 1, congratulations. Yes, sir. For what? Right now? Yeah, just put on this. Okay. Now, you've gotten 1. Let's say Maya comes by and gets the first bag. Okay. What if Tanaya tries to come and get my second one? She may pull back a nub. Okay. Why? How does it translate to this? My first one you just got required this much, but what happens when you get to the second one? The more electrons removed requires more energy. Well, what happens if I, let's say, take it all the way down to barium, and I've got 2 bags sitting way out here? Both are gone. Do you agree it's a lot easier to do that? Okay? What happens when I add a 3rd bag and I've turned into aluminum? Okay? Is it going to be harder for me to protect all three of these? Now, you've also got to remember, what are these bags of Cheez-Its doing? They're spinning around me. Yes, sir. Aluminum is group 13, so it's got 3 valence. Okay? So, again, the thing about it is, even though I'm adding more electrons, is my Zeph increasing? So what's really happening to the distance? They're really starting to get closer to me. To the point where if I add a 4th one, no, that's it, I'm out. Okay. But it's going to eventually get to the point where if I've got 7, I'm going to keep them so close to me, you're not going to be able to get to them. And so that's the concept that I want you to see, is that I'm going to be able to try to hold on to these things as much as possible. And that's the whole goal. So hopefully that made you hungry and got the point across. I'll be eating those for lunch today. No. All right, electron affinity. So this is the second thing I want to talk about today, and we're going to stop after this one. Does anybody know what the Greek... What does affinity mean in Greek? What? No, it doesn't mean bond. You did try. It stands for love or like. Aphrodite, the goddess of love, she has an affinity for things. Okay, so what is electron affinity? The love of an electron. So it's your ability to attract an electron. And once you attract it, it's your ability to hold on to it. Okay? So, the third importance of bond formation after size and ionization energy is the energy change accompanied by the what? Attachment. Highlight that word. Attachment. What does attachment mean? The gaining or sticking of an electron. Does group 1 have any affinity for electrons? Why? They want to get rid of it at all costs. What about group 17? They have a severe desire. Almost, never mind, I'm not going to say that word. Nothing. Have an attachment for electrons. The key word here, and again, it's an attachment to a neutral atom. So it's out there by itself, and it's neutral. Exactly. The energy change that occurs when an electron acquired by a neutral atom is called electron affinity. Again, it's the love of attachment. How much do you have a desire to go have an electron attached to you? In many cases, electron affinity is positive. Again, energy is going to be added to you, signifying that energy is indeed released when an electron attaches to an atom. Okay? Now, there's going to be a lot here, and I'm going to try to sum it up very, very simply. When an incoming electron enters a vacancy, do me a favor, put quotation marks around the word vacancy. What does that mean? It's empty. There's a space available for it. How many available spaces does group 17 have? It's got 1 available space. So do you think there's going to be people out there battling for that emptiness? Okay? In the valence shell of an atom, although it is repelled by the electrons already present. Circle that, and up here, please write this. What are those core electrons doing? Shielding. Perfect. They don't want you to join them. They're going to try to push you out as much as possible. However, it is sufficiently close to the nucleus for there to be a net attraction. Why would there be an attraction between a nucleus and an electron? Very good. You have positive and negative attraction. Hence, the energy of the electron is lower when it is a part of the atom than when it is not. The electron also has a desire to be attached to the atom itself, so it's going to have less energy because it's basically spun itself into the atom. However, if the incoming electron has to start a new shell, let's look at it from this perspective. Fluorine. Do you agree it's got 2 electrons in the first one? How many does it have in the second one? How many does it have? 7. 1, 2, 3, 4, 5, 6, 7. So it's got how many vacancies? What is it going to do to get that 1? Anything. Here's the weird part. Let's pretend that 1 joins in, and then all of a sudden we got this other one that wants to add an energy level. Does fluorine want that? Not at all. Okay, because now fluorine has just skipped the noble gas and went into sodium. Fluorine doesn't want this. So this is why it says, however, if the incoming electron has to start a new shell because of the orbitals of the neutral atom are full, then it remains so far from the nucleus and so strongly repelled by the electrons already present that there is a net repulsion, and energy must be supplied to attach it. So, if I wanted to make this happen, would I have to force fluorine to accept that electron? Yes, it's not going to do it on its own. I'd have to force it to do it. In such cases, the electron affinity is negative, which means energy has to be applied. And so here's the way that we can sum all of this up. Can y'all see that? Rare, which means it never happens. It does not happen. Okay? It does not ever happen. Okay? All right, so here's our trends. We need to talk about our trends. It's very important. Affinity generally increases across the period, which means they have a desire for them to attach. Well, again, you can learn a trend, but you got to know why. Increasing nuclear charge. What is another way to say nuclear charge? Zeph. You see a theme always popping up. As we move left to right, our Zeph goes up. Atom gets smaller. It has more of an affinity for an attraction. The closer the electrons are to the nucleus, the harder they are to steal them. I want you to add a bullet and say needs to fulfill octet. Add that bullet for me. Need to fulfill the octet. Okay? Now, again, the electron affinity generally decreases down to groups. The larger the electron cloud, again, distance matters. The farther away the electrons are from its nucleus. Again, just like I used with the electron, with the Cheez-Its, the farther out it got, the harder it was for me to hold on. And plus, I want to get rid of it. I don't want it. It can just go away as far as I'm concerned. No, I do want Cheez-Its. Okay? All right, we'll stop here for today. Well, I'll finish this up tomorrow.